We have a curve that is produced by the point P moving counterclockwise along this polar curve in such a way that the line segment OP makes one complete revolution. That is, the line segment OP makes one complete revolution so that the angle theta goes from 0 to 2 pi. We need to sketch the curve and we need to find the total area swept out by OP as it makes the revolution. Sketching the curve is necessary to solve this kind of a problem even if we are not given the instructions explicitly to draw or sketch the curve, but here we have been given those instructions explicitly. So the point P starts, let's say, over here, or let me put it a little closer, over here, where r is equal to 1. Let's just mark this as 1. And then at this starting point we have that our angle is equal to 0 and our r is equal to 1, which fits. It fits that r as a function of the angle is equal to e times the angle over 2 pi. And we can see that as our angle increases, so does our radius r, and it increases much more rapidly. So actually it's not actually possible to draw this in scale. So we are only left with an approximate sketch. So here let's draw our curve. It's a spiral with increasing r, and here is the segment of the spiral that we need. We made a complete turn. The angle goes from 0 to pi over 2 to pi to 3 times pi over 2 and eventually to 2 pi. So this is our point P over here, and we can call this point P prime, which is the final destination of the point P after the line segment stretches and makes one complete revolution. So we have sketched the curve. Now we need to find the total area swept out by the OP as it makes the revolution. Obviously, trying to calculate the total area, that is trying to integrate and find this area and find this area over here, would be a very difficult task if we were to work in the Cartesian XY coordinate system. But if we take a look at the polar coordinate system with dimensions theta and r, we see that r is a monotonically increasing function of theta. Therefore, it's going to be quite easy to find the area in terms of polar coordinates. But of course, first we need to transform everything that we need. So we go between the Cartesian coordinate system and the polar coordinate system. X is equal to r times cosine of theta, and y is equal to r times sine of theta. We know this. In order to calculate our area using the polar coordinate system, we will take a look at a small segment of the area. Let's take a look at this segment over here. We treat it as an infinitesimal segment of the area dA. So our dA looks something like that. It's actually a circular segment. Here is an angle d theta, which is infinitesimal. And here we have radius of the circle r. In this case, of course, r is a function of theta and it depends on theta. So our unit area, dA, is actually the area of a segment of a circle. So we have an area of a circle, r squared times pi, multiplied by the ratio of our angle and the full angle of the circle, which is 2 pi. And this is obviously r squared over 2 times d theta. So our total area is the integral of all unit areas, in this case from the initial angle 0 to the final angle 2p. That is, once again, we must express the area in terms of the angle so that it makes sense. So we have r squared over 2 times d theta, where theta goes from 0 to 2 pi. And we plug in our expression for r over here. Let's place 1/2 outside of the integral. Let's place the bounds on the integral. And we have r squared, which is e to the power of theta over 2 pi squared. So it is e to theta over pi. We integrate it over the angle d theta. Now we'll make a substitution. Let's not forget this 1/2. And we substitute, say, t is equal to theta over pi. And we have that d theta is equal to pi times dt. So we have pi over 2 times the integral of e to the power of t dt. We must be mindful of the boundaries of the integral. When theta is equal to 0, then t is equal to 0 over pi, which is 0. T is equal to 0. And when theta is equal to 2 pi, then t is equal to 2 pi over pi, which is equal to 2. So we have pi over 2 times e to the power of t, where t goes from 0 to 2. And that is pi over 2 times e squared minus 1. This is our area swept by the curve.